let's start. I'm again here to talk you about, to give you a brief introduction about the DRIHM portal that we will experience since this afternoon. Here I will propose you an introduction about the concept of Science Gateway, just to make you understand that the DRIHM portal is the science gateway that we are developing for hydrometeorologists, researchers and users, of course. I will introduce you the approach we had in the development of the portal, so the technology we used to develop it, what is actually the portal. So in integration of all the pieces you are looking around, you are experimenting in these days, and we will show you how the portal exploits the technologies we employed for the development of the portal itself, and what is behind the interface in terms of workflows. What is behind the interface instead in terms of computational resources will be explained, pointed out in the technicality lessons that you will have in few days, the day after tomorrow, I suppose. So, let's start with the definition of Science Gateway. The Science Gateway are community-based developed tools, applications, services, data that have been integrated for the specific community. It is usually provided to the community using graphic interfaces that have been further customized to meet their requests, their requirements. Usually, these interfaces have been figured out to configure to have a good use, a proper use, an optimal, if possible, use of the tools, services, resources they are going to provide. Thus, to enable all the community to use these resources without actually be aware of that, let's say. In this way, researchers can focus on the science and not on the infrastructure. I think that if you think about what you saw up to now, the models, the meteor models, the hydro models, they show you how to configure parameters. Some of them for sure, some of the teachers for sure, showed you the portlet we developed. I'm now going to introduce the word portlet. So the interfaces we developed in the portal to enable you the configuration, but none of us up to now has talked to you about how to put together data, how to exploit resources, because this will not involve you. It is made by the portal. And I'm going to say in a very brief, very high level manner how we do it. So, the definition for the Science Gateway, I took it by the XIDE site. XIDE is a US project that actually developed Science Gateway. Actually, the first time that the word Science Gateway showed up was for TeraGrid, so probably 10 years ago, more or less. That is again a US project about grid computing. We can say that in some sense, the Science Gateway are, from a certain point of view, a sort of evolution of the DRIHM grid portal, because they provide more and more facilities, and we will show you it, especially in terms of computational resources, since grid portals are portals that provide you through graphical interface and so on, access to grid resources. You will see that the infrastructure that is behind the portal is more and more rich. We have actually an heterogeneous infrastructure to manage all the requirements that all the model we are providing pose to us. So, going back to the concept of Science Gateway, what we can point out, that we have a set of innovative services that hides the complexity of the infrastructure itself. So all the users that for sure are scientists and not computer scientists, are not experts, are never experienced probably this kind of complexity as infrastructure, and so they are on the safe side. They don't need to do it. They can simply use the Science Gateway. And the Science Gateway supports a variety of community-specific capabilities, workflows. That is what we are going to doing when we chain models. Virtualization of software or resources, also this feature is present in the DRIHM project. Visualization, we had a talk this morning, and all the part related with the resource discovery, job execution, access to collection of data that can be seen as our critical cases, the repository, the application, the tools are completely managed by the Science Gateway. And so, I think that it is clear that although a Science Gateway can be provided as a set of web interfaces, is it actually more and more than a web page? And as I was saying at the beginning, the DRIHM portal represents the Science Gateway we are developing for HMR community. It is more than a simple interfaces. It provides you the integrated solution we are developing in the DRIHM project, enables you to enables us as developer actually to manage the DRIHM infrastructure at different levels. We have different kind of users, we have different kind of workflows, we have different kind of data and services. And it enables the exploitation in a transparent manner of all the resources that we are going to use in the DRIHM infrastructure. I already told you that we call this infrastructure as DRIHM Distributed Computing Infrastructure, so this DCI, since I think that from today on you could listen to this word, I could simply recall it to you. So, to develop the portal, we adopted the approach proposed by the CIBAS project, that is another European project founded by EU community in the 7th FP7. And CIBAS is proposing methodologies to customize general purpose portal families that are developed through GU's WSP grade technology. So we are using this technology to develop the portal. The technology is GU's WSP grade and has been developed, actually is always under development at the Laboratory of Parallel and Distributed Systems in Budapest, Hungary. Here there is the link to the group that is working on this stuff. So we customized this generic solution thus to achieve a solution for the problem posed, the specific requirement posed by our community. I would underline that the portal represents for a common user the only way that you have to access all the resources that we provide in the project. And as you already know yesterday, and we have to learn also today, in order to access and use just such resources, you need to be a DRIHM user portal, you need your certificate, and you need to subscribe to DRIHM VO. Just to give some detail more, but not too much, about the technology we use. The architecture is composed of 3 different layers. Let's start with the lower one, the architectural and middleware tier. That is called the DCI bridge, so distributed computing infrastructure. And it is implemented to manage the job submission. This layer provides you an abstraction from the different infrastructure that it is able to manage. I have them in the next slide. And it enables you to access a large number of available infrastructure. So what it means, that if I want to use one of the infrastructure that the DCI bridge supports, I don't need to develop a piece of code to enable the job submission. I can simply use what they provide. So it is quite comfortable, let's say. And the infrastructure that is possible to access through this layer of the GU's WSP grade are remote cluster, local cluster, let's say. So let's say out from the grid, from the cloud, and all this kind of ICT infrastructure. They support two local schedulers, that is PBS and LSF. For all the other, you have to develop your code by yourself. Supports several middleware of grids as Glite, different version of the Globus toolkit, and Unicore. Enable you to access supercomputers, as for example with the Unicore, that in Europe is possible. Enables you to access desktop grids that are a grid-like system made up of simple laptops or PC. It is the evolution of what was called volunteer computing. And it also enabled you the access to cloud infrastructure, as for example, the cloud broker platform. Moving to the second layer, we have the middle layer. The middle layer is provides the GU services, and is mainly related with the actual management of workflows. We can say that a workflow is a wrapper of a code or of many code if we have a workflow composed of different models. In few slides you will have an example. And in our case, those are our models, possibly connected with the bridges we are developing to achieve the standard compliance of our interface, the ones that you listened this morning and you will listen tomorrow more in detail. And this layer provides you the functionality to create, manage, execute, and monitoring your workflows. Actually, this layer is not actually experienced. Indeed, this layer is not actually experienced from normal users. Let's say that those are experienced from developers. In fact, the interface, the tier that is always usually experienced by normal user of this kind of architecture is the presentation layer. So the layer with which WSP grade presents its capabilities. That is a graphical user interface. And it is actually a web interface to access all this facility and to exploit the DCI bridge and so on. So the interface is made up of what is called a set of portlets. Each portlet is a web module that is reusable and has to be deployed through a container. The container that has been chosen by WSP grade architects is LifeRay. I don't know if you are familiar with this kind of tools. And at this point, I will leave the floor to my colleague, Emanuele, that will continue the presentation, give you more details about what the portal actually shields.
Okay. So the general usage of GU's portal requires that each node in the workflow contains all the information. So essentially, we have to wrap in each single node all the input, all the outputs, and all the binaries required. For instance, for running a large meta model, we have to wrap completely WRF, for example, and associate to one of these nodes, to one of the input port, all the binaries that I'm going to execute, all the input files and so on. This means that for running a chain composed by large models, we need to load on the portal every single time such big application. Again, running WRF may require for libraries and main applications on hundreds of megabytes of binaries. Input file again are large, and all the tricky parameters, like if I want to submit on a resource like a grid resource, I have to specify the kind of language I have to use to talk with the resource. The name of the resource is the location, again, the binary file, all the parameters that are required to trigger the execution. Okay, our idea was to hide this complexity so the user can focus on setting up experiments. And on the other side, we have to keep a working copy of the application somewhere, keep input and output file in a repository, so that each grid resources is able to fetch the application, fetch input file, combine everything, trigger the execution, and store back the output somewhere else. So essentially, instead of keeping this interface that is very general, we can produce a workflow composed by up to hundreds of nodes with an arbitrary set of input and output ports and so on, but really complicated to use. We prefer to put a layer on top of the GU's presentation layer that is customized for our community. So again, some tricky details may also be different from a computational resource to the other one. This was the reason that drove us to design an additional layer on top of that. To go a little bit more in detail of the parameters required to run the application, essentially those parameters drove us to the design of the architecture. For each model, we have to specify a set of ports. A port is a way to communicate with the application. In this case, again, this example is for WRF. We have a first port that is getting the name list, so the execution parameter, but also the binary and the output of the preprocessing, so the metgrid that is ready for WRF execution. Moreover, we have to list all the outputs. In this case, we are getting a single output from WRF, and we are fine. In case we want to execute different model like MesaNH that is able to produce an ensemble, we have to produce a workflow with a variable number of ports, one port for each output. So even the geometry of the workflow has to be adapted to the single experiment. And obviously this is a further problem when we want to share an infrastructure to people that are not interested in playing with such generic tools, but they want a solution to to their experiments. Our solution is to have those portraits. The portrait is able to create the name list, and this is also a little head that we give them. Instead of focusing on the number associated to the microphysics and so on, a simple GUI can help the user in producing a syntactically correct name list. Then, if an experienced user wants to play more with the name list, edit it and so on, he can do that. but we can support the user at least for getting a first draft of the name list. Moreover, the binary application has to be stored somewhere. We created a binary repository. When we submit a job on a resource, we try to synchronize the resource with such binary repository. If the application has been updated, we get the most recent version and play with it. So we guarantee to the user that each update on the application is always synchronized, so we don't need to check, oh, I have the last version, probably the bug that I experienced last month can have been fixed, where I can fetch the application and so on. Everything tested working is on the binary repository. So essentially, this is our approach to job submission and to to improve user experience. Up to now, we are relying on GUs. GUs implemented in DRIHM Portal is this version 3.6.3. They are moving fast. They are releasing a minor version nearly each month, and the newest releases are a little bit better in terms of new standard, like they move to a newer version of Java, to newer version of some security libraries and so on. But those versions are not very stable up to now. So we are continuously testing for porting the portal. As soon as the portal will move to newer version, we will be able to support higher security, so newer certificate will become usable, and also we will be able to submit to a wider spectrum of resources, like supercomputing resources hosted by Exceed, that up to now are not available. The idea of using a high-level portlet for supporting a user drove us also in the adoption of some APIs that are exposed by GUs. These APIs, ASM, are a way to connect directly high-level user interface to the workflow and trigger the execution of the application. So instead of relying on the graphical user interface already available, we created a direct connection to the engine behind the GUs. So essentially, this is the structure of the portal as we are using now. Those two layers are provided by GUs. This is part of the portlets that is exposed by GUs, but we are only relying on the security portlet that is helpful for handling certificates. And all this part has been developed within the project. We will focus on model-specific portals. For sure you have already saw something, but today we will play a little bit more with such model-specific. The portlet structure is also flexible, so in case we want to add an additional model, we can just collect the required information, build a component that is specialized for the new model, and plug it in the overall architecture without the need of rebuilding the whole model and so on. On Thursday, we will also analyze a little bit the model-specific administration, so the ability to create new model instances, so models that are calibrated to be executed on a particular domain. Okay, just to summarize a little bit what we saw. The DRIHM portal is our solution for providing a scientific gateway to the HMR community. The main idea was to hide the complexity of the distributed computing infrastructure and support the user in the definition of their experiment. The job submission is something that we are inheriting from GUs, and so is not really one of our contributions. If you have questions, probably we have a little. I think that we will have time to check and experiment just after lunch, because we are going to have a practical session at 3, so probably if some questions arise in your mind during the lunch, we can use the time later. Okay.